Next, we move to the question of oxidation-reduction reactions. This was a very important part of Chapter 2. Chapter 2, of course, looked at atomic and molecular structure. It looked at the balance of chemical equations. But one of the most important aspects turned out to be studying how electrons delocalize in a molecular bond. A perfect case in point involves CO2. So if we start with carbon and oxygen atoms apart from one another, they, when brought together, form the carbon dioxide molecule. But the carbon dioxide molecule is a carbon atom in the middle with two oxygen atoms bonded into that central carbon. And when we look at the way in which those electrons delocalize to lower the energy of that molecular structure, we realize that two electrons have migrated from the central carbon to the outer oxygen. And in a similar way, two electrons have moved from the central carbon to the other oxygen at the end of the molecule. So that allows us to think and clarify what it means to establish oxidation states and oxidation numbers. Now, when we establish those oxidation numbers for a molecule, we first look at the metals in the first and second column of the periodic table, because, as we know, those metals have a very, very weak capability of retaining those electrons. So in any molecular structure, an electron is going to move from that metal to whatever other atoms are in the molecular structure. Now, when we move to nonmetals, which is the case for many, many examples, we have to be very careful about the ordering by which we assign those oxidation numbers. And the ordering here is important because the strength of a given atom to attract electrons in a molecular structure is a very important hierarchy. And at the top of the list is fluorine. And as we'll see when we study quantum mechanics, fluorine has a tremendous ability to attract electrons. And when it attracts electrons, that means the charge of -1 moves from whatever atom there is in the molecular structure to fluorine. But look what happens next. When we're assigning these numbers, these oxidation numbers, hydrogen is in the second position here. And its oxidation number is +1. That means that an electron has moved from hydrogen to another atom in that molecular structure. Next comes oxygen, and then following that in order is group 7, 6, and 5. So let's look specifically at what this means for carbon dioxide, because whenever I'm assigning oxidation numbers in any molecule, I always go back and remind myself carefully what the oxidation numbers actually mean. So let's do that. We have a carbon atom in the middle of this molecule, and we have oxygen atoms at the two ends. And when those atoms are free in space, their oxidation number is 0 because they have neither received nor given away an electron. Now, when we form the bond, the electrons delocalize from the carbon in the center to the oxygens on the outside, and we can see that immediately because we have no fluorine, so we ignore that. We have no hydrogen, so we ignore that oxidation number. Oxygen is the next, and oxygen has an oxidation state of -2, and that means specifically that two electrons have moved into the orbital domain of oxygen, and of course through symmetry exactly the same thing happens to the other oxygen. But that means we have an oxidation number of -2 for oxygen, but that means that 4 electrons have been removed from the central carbon, so its oxidation number is +4. And it's always important to remember and go back and remind yourself exactly what it means when electrons delocalize from one atom to another and how that affects the oxidation number given to that particular atom.